Hi everyone. Hope you are doing great. Okay, so let's get started with today's lecture. So today we will see that a linear algebra perspective, or you can say a different perspective of the same problem that we were solving. So what we were trying to solve, let me just quickly remind you. We were saying that suppose we have some data, right? Suppose we have some data and there is a corresponding label for that. For example, for example, let's suppose the data is having multiple x or multiple x1 x2 x3 something like that, right? So suppose this is first feature, so it could be 2, this is 3, let's suppose this is -1 0, okay, 3 5, this is 11, this is 6, this is 9, this is -6, this is 3, okay, anything, this is 0 1, -30, -3 or -30, let's suppose 7 and 11, okay, and something like that, right? And then you have, let's suppose this is 1, this is 5, this is, let's suppose, 0, this is 7, this is, let's suppose, -2, okay, something like this. Suppose you have some data and there is some y label which is given to you, right? So the data could be anything. I mean, the data could be of your ice cream sales, or the data could be of any other domain, right? So data could be anything, but there is a y associated with this, right? Suppose the labels are maybe, let's suppose this is 30, this is 35, this is, let's suppose, 40, this is, let's suppose, 42, this is, let's suppose, 45, right? So there are some labels associated with this particular data, or some y values associated with this particular data. Now what we want that, okay, we want to solve actually all of these equations simultaneously. But these are, let's suppose, too many equations, which means you have many data points. In practical, what do you think, that number of rows will be more or less? Let's suppose I have one year data with me. I mean, 1 year data means that 1 year data of ice cream sales. Let's suppose I have 1 year data with me. So how many rows will be there if I have 1 year ice cream sale data? Then I have, let's suppose, for each day I have just one row, okay, then 365 rows, okay. Let's suppose we have 365 rows, okay. So in general, do you agree that we have, in general, many rows, okay? In most of the practical applications, what do you think this number could be? Any guesses? This number of rows in many of the practical application. By the way, what do you think? The more is good or less is good? Which means if I have just, let's suppose, three, four equations, everything is sweet, nice, right? So do you think it is good or more is good? More data is good or less data is good? What do you think? Obviously more data is good, right? If you have more data, then you can do the predictions better, in the better form, right? So data is money. Okay, yeah, like, if you are selling it then it is money. Anyway, yeah, it can make you money now, for sure. So basically more data means better models. Actually, you can better understand the problem, right? So definitely we want more data. But just assume that you have, in a room, let's suppose you have many people. In a room you have many people. Do you think, or there are many students, okay, let's just assume in a classroom there are too many students, okay. So these are the students. So do you think, like, I'm just asking you, do you think that if I have, let's suppose, three four students, do you think it's easy to, manage the harmony, manage the peace? Or if there are, let's suppose, thousands of students, then it is easy to manage? Obviously, if there are thousands of students, then they will make noise, right? I mean, they they will be like it is very difficult to keep the balance if there are thousands of students, right? So basically, if there are thousands of rows, okay, then obviously it is very difficult to make them collinear, in the sense that there may be somewhere here and there, right? If this is just three and four, then yeah, maybe you can have, the solution of Ax equal to b if this is just three and four. But if this is just too much of data, then it is almost impossible to have collinear data, right? Do you think it is possible, like always possible, if you have too much of data? Do you agree that सबको एक साथ ले चलना, like keeping everyone on the same track or on the same way, it's very much difficult. So basically if you have too much of data, then intuitively I'm just asking you, intuitively, okay, I'm not asking you mathematically, intuitively I'm just asking you, let's suppose this is the four columns. So you will be having, let's suppose this is the column number 1, x1, x2, x3, x4, okay. Then you will be having, let's suppose some equation I'm writing in the vector form. So y cap, okay, you will be having ax1 plus bx2 plus cx3 plus dx4 plus e, something like this, right? I mean, you will be having something like this. So basically, okay, it will be very difficult, right? Or maybe if I just say it why, it will be very difficult to find out the to find out the coefficient a to e such that they get you e y, right? Don't you think? It will be very difficult to maintain that harmony among all of them. Agree? Right? If these are, see what I'm trying to say, if these are just 3 4 rows, then yeah, then maybe you can have linear combination of this much data and this column. Maybe the linear combination of these 4 columns is this column. But इतने सारे हैं, कहीं तो inconsistency आ सकती है, isn't it? There might be some inconsistency. Right? See, if this is this much only, then most probably it could be, I'm not saying it will be, but it could be, you can say consistent, right? It could be consistent. If this is just 3 4 rows, could be consistent. But if there's too many rows, do you think कि सबको एक साथ लेके आगे बढ़ना is very much practical? So there will be inconsistencies, right? If there are too many rows, so you can say probably let's suppose you are calling this as ax, I mean linear combination of these columns, let's suppose you're calling as ax, then probably you might not able to solve this ax equal to b. Let's suppose this is b. Okay. If these are the too many rows, then probably ax equal to b might not be solvable. So in other words, if I just talk in terms of the linear algebra, if this is a is, you can say tall, right? Thin and tall, which means something like this. If a is thin and tall, right? Then this b might not be, I mean, that much easy. You agree? Whatever b you are getting, that this particular set this particular system of linear equation, maybe you can say this particular system of linear equation may be inconsistent, right? So it is generally the case, see, I'm not having any mathematical claim or something, like it is, I'm just asking you intuitively. So it is generally the case, if a is thin and tall, then ax equal to b is inconsistent. So generally I'm saying, okay, so generally, so if a is thin and tall, something like this, right? Quite thin and tall, something like this. Then generally, ax equal to b is inconsistent. Do you agree? Okay, there is no mathematics I want to go. I'm just saying, right? So basically, see here that I have some data and I want to finally get this y. So this is like linear combination of columns I want to take, and I want to finally get this b or y. Then one of the ways that we do the optimization perspective, in the sense that we write the loss function and then we do the differentiation and then we find out the the minimizer of that loss function. For example, what will be the loss function? Can you tell me? See, I want to minimize the difference between ax and b, right? Ax is some vector and b is some another vector. In the vector format, you can say I want to minimize the difference between ax and b. So I want to choose x such that ax minus b difference is actually minimized, right? I want to minimize this. Is this okay to everyone? Okay. So which means ax minus b whole transpose into ax minus b. I want to minimize this. So if you minimize this with respect to With respect to what? With respect to x, right? So basically I want to say that suppose we have some linear combinations that are given by x, then I want to choose such x which is having which is making me ax such that ax and b are least far from each other, okay, which means they are very near to each other. I want to minimize the difference between ax and b. So I want to choose such x, right, which means I want to minimize this particular function. So if you differentiate this, then what was the gradient? It is 2x x transpose, 2x x transpose. And if you take one more time transpose, we have done it earlier also. So it will be something like this, right? And then if you make this gradient to be 0, then it will be A transpose AX equal to A transpose B. Is this okay to everyone? Okay, let me know. Okay. So basically, I want to choose x such that it is a solution of this particular equation. But today we will be seeing something that will also arrive to the same conclusion, but without using the calculus. Okay. So let's just see that. So this was the story of yesterday. Now, now, see here that what if we can't solve x equal to b? How we can solve it as closely as possible? For example, if all the points are not able, we are not able to fit on the line, then what we will do? We will be finding the best possible line. Okay, okay. Can you please repeat tall one on last slide? Which one? This one? This one you're saying? Okay, so I'm just saying that if this is A is having too many rows, okay, generally I'm saying if it is having too many rows, okay, too many rows, then it is very much possible that is it like maybe some of the row could be like this. You may make do you remember the from the linear algebra what is the condition of inconsistency? All zeros and then there is some non-zero, right? Right? In linear algebra we have studied it, so that's fine if you don't remember it. So basically, if there are too many rows, then obviously there could be a chance that you may be having all zeros and non-zero, this kind of thing, okay, this kind of thing you may be getting. Or in other words, if there are too many rows, then it is not possible to solve all the equations perfectly, right? I mean, this is just one intuition I wanted to convey. Even you have not got it, it is fine. Yes, obviously it is better to have more data, right? And we want to solve for more data only. So suppose that we have ax equal to b, right? And then we have this suppose we have some data and we want to solve for x equal to b. So suppose we are not able to solve, which means this particular data, whatever the data we are having, we are not able to fit it on the line, right? Then how we can solve it as closely as possible? Let's just see this. Okay. So one of the ways that we can use the optimization point of view, but today I want to check linear algebra point of view. Okay. So before that, there is a quick detour that I want to take from the linear algebra, and then we will just see what is the orthogonal projection, and then I will come back to this particular slide. Okay. So, but there are some questions. Let me just quickly take. Navjot is saying, sir, is it that too many questions? It is difficult to have common point of interactions. Yeah, and whatever, yeah, you can say something like this, that if there are too many equations, yes, you can say something like this. Yes, that is also true. Okay, that's true. Suraj is saying, sir, while we are finding the best fit line, we're always considering a straight line. Is it necessary to consider a straight line as best fit line, or any equation we can take? If we have another, what is the criteria to choose? Okay, so we will come to the polynomial and these things. Okay, currently we are talking about the straight line. Actually, like it won't matter much. Okay, like we will come to those things again, right? Later on, we will come to those things. Okay, what if this is not a straight line? So actually, like there is something called feature transformation. So instead of x, you can convert that. I mean, you can instead of having x1, you can have x1 square, and you can call it a different feature. Okay. And then if you want to quadratic, see, I mean, I'm just telling you quickly. Let's suppose the quadratic equation may look like this. Okay, let's suppose this is the quadratic equation that that you want to fit. You want to fit a polynomial. So this can also be done using the linear regression, in the sense that instead of x1 you use x1 square, and let's just say that, okay, this is a, new x1. This is a new x1. No one cares, right? This is a new x1. You can say this is a new x1. We will talk about this feature transformation and these things later on. So let's just continue with the straight line fit. Okay. So Sriyansh is asking something about the overfitting. No, Sriyansh, this is wrong, and let's just not go into that, because you might not be knowing what is overfitting. More data doesn't mean overfitting. Okay, more equations, more data does not mean overfitting. Overfitting has altogether different definition. Okay, great. So let's suppose this is a quick tour to linear algebra. Let's suppose I have one vector b, and I want to project that vector b onto this vector a. Then what will I do? So projection means that I basically I want to represent the b in terms of a, which means that I want to write. Okay, I want to write something like some scalar. You can say c a. Okay, I want to write b equal to c a. Can you write directly b equal to c a? I mean, B is in another direction, A is in another direction. So obviously, geometrically, as you can see in this picture, it is not possible, right? B equal to C is not possible. But I want to write in the sense that I want to, project this B on the A, and the projection will be in this form. So basically, what I'm trying to say, that let's suppose you have a vector B, and you want to project that onto the vector A. Then this projection, let's just call it a small p or something. This projection you can call it ca, right? I mean, that will be in the direction of a. Okay, and I want to find the value of c only. Okay, this is the task. So for example, this is b, this is a. I want to project b on a such that this p is ca. Okay, or maybe I think they have used x, so let me just use x. So xa. Here, this x is scalar or vector? Tell me. Or maybe I think they might have used x cap. So x is a scalar, a is a vector, and p is a projection of b onto a. Okay, because it is just ca. Instead of c, I'm just using x cap. Okay, you can use c, doesn't matter, but let's just use x cap to be the consistent with the literature, or with the books. Is this fine to everyone? Okay. Okay. So, what we can do, see here, that the projection is defined in such a way that this vector b, and this vector a, if you put a perpendicular line from the head of this b to a, then it will be like this. Okay, and this is how the projection is defined. So basically, this angle that we are currently talking about, this angle is 90-degree angle. Okay, so this is 90-degree angle. Okay. So, what you can say, that this P, and then if you make the diagram correctly, this is P. This is the vector which you can call, this is B. So basically, this is, you can say, B. There is one more vector which is P. This is P. Okay. Can anyone tell me what is this vector? What is this vector? So P plus this should be giving you B, right? So it will be B minus P. There is a triangular law, right? It will be b minus p. So this vector is b minus p. So you can say, and p is actually x cap a, and our ultimate aim is to find what? The projection. Projection means this x cap a. Do you have already a? Do you already have a? Yes, right. I mean, a is a vector on which we want to project on. So a is definitely with us. What about x cap? X cap we want to find out. So what is our goal? Our goal is to find out x cap, right? Is this fine to everyone? Let me know. This is our goal, right? Now, I mean, now once we find x cap, then obviously we will be finding this p, right? I mean, the ultimate goal is to find p, the projection. But let's just first find x cap. Okay. So what we can say from the geometry, we can find out x cap very easily. We can say that this vector, which is b minus p, right? It is perpendicular to which vector? A, isn't it? So P is nothing but x cap A. So you can say that A transpose into B minus x cap A. The dot product of A and this particular vector will be 0, right? 0. So hence, uh, x cap which is scalar. So you can say x cap A is equal to A transpose B. Uh, I think I did it correctly or there is something wrong. Sorry, this is A transpose B. This is not just x cap. This is basically uh, x cap into A transpose A. Okay. I mean, this x cap is a scalar. You can write it. See, if you multiply these two, I hope you got it. You will be getting A transpose into x cap into A, right? A transpose into x cap into A. It is a scalar. X cap is a scalar. You can write it here. You can write it here. You can write it in between. Doesn't matter. So I'm just writing it here. A transpose A. This is a scalar or vector, this particular quantity. And this particular quantity is scalar or vector. Both are scalar, right? Both are scalar. So you can get x cap. Let me just move to the next slide directly. I hope you are able to understand that it is very easy. I mean, this particular, see, we will be going to the multiple dimension. Currently, it is just one vector, but we will be going to the multiple dimensions. So this particular vector, okay, it is perpendicular to this A. That's the only theory we have used, right? This is the little geometry we have used. Actually, we will be using such kind of geometries here and there. Okay. In machine learning, we will be using this triangular law. Okay, this vector is perpendicular to this vector, and using those little observation, we will be finding few values. Okay. For example, given this, we are able to find out the value of x cap or maybe the value of projection. So x cap or okay, sorry, they have used x or x cap. I'm sorry about it. Actually, like this is up to the literature. Some people use it x cap. So I thought that, okay, in the slides I have x cap, but that is x, which is fine. I mean, I hope the notation is okay to everyone. Okay. So some people use some x cap, some people use x. So I thought that we are using x cap. Okay. So is this fine to everyone that how we are finding out this x, which is A transpose B upon A transpose A? Suppose this A is a unit vector. If A is a unit vector, then in that case, can anyone tell me the projection, by the way, is AX or XA? I mean, this X is a scalar, you write it here or here, doesn't matter. They're writing it with their own choice. Okay. So if A is a unit vector, then what will your X? Your X is just A transpose B, right? Dot product between A and B, isn't it? The dot product between A and B. Okay. Okay. So I think some of you guys are having doubts. So let's just quickly do it. Can you take pen and paper and just try to do it by your own? Because I hope that's easy enough to do it. So see here, this is B, this is A. This angle is 90 degree. Okay. This vector is B minus A. You just need to apply, sorry, B minus P. You just need to apply that B minus P is perpendicular to A, which means dot product of both of them is 0. And where P is nothing but some scalar into A. Now tell me, till now, is everything fine? Whatever I have written I have, on the slide? Till now is everything fine? Okay. So okay. So till now everything is fine, right? So I want to project B on A, and I observe that okay, B minus P is perpendicular A to A. So this is the observation that you need to make, right? Okay, why B minus P? See, this is because of the triangular law that this is P, whatever vector this is, okay? This vector plus this vector should be adding up to B, right? For example, let's suppose this is A, this is B, right? Can anyone tell me what is this vector? This vector will be A plus B, right? A plus B. Okay. This is called triangular law of vectors. Triangular addition, I think. Okay. I don't remember exact name, but I think this is called triangular addition of vectors. Okay. So whatever vector you take it, summation of this and this should be giving you B. So if you take it, let's suppose for example T, then P plus T should be B. So T will be B minus P, right? Okay. So this is the important observation that you need to make. Right. Now after that it is easy. You just put the value of P. Dot product means either you take the transpose of this into A or A transpose into this, doesn't matter. So I'm doing A transpose because A is a easier term to write the transpose. This is X A, right? Okay, equal to 0. From here you will be getting X as A transpose B upon A transpose A. This is your X. Is this X whatever we are getting? It is a vector or a scalar? Whatever X we have got, is this a vector or a scalar? This is a scalar, right? Is this a projection? Is this a projection? No, right? Okay, Anurag is asking that why this is perpendicular, because that's how the projection is defined. If you want to take the projection, you need to draw the perpendicular line to the vector on which you want to project. Okay. So this X is not the projection. What is a projection? X into A is a projection. Okay, X into A is a projection. So the projection is this P. Now, now uh, I hope you understood that the projection is P, which is given by A into X, and X is A transpose B upon A transpose A. So if A is unit vector, then X will be just A and B dot product between A and B. Okay. So X is basically, you can say that, okay, in other words, if I just ask you that, let's suppose if A is a unit vector, then dot product between A and B, can I say that it is a projection? The dot product between A and B is a projection. A transpose B is a projection. Tell me. It's a projection of B on A. True or false? Obviously, this is false, right? This is false because it is not a projection. Projection is A into that scalar, right? A into X. This is projection. Okay. So this is false. What is the projection? Okay. This is projection, which will be A into A transpose B. This is projection. In in the second question, if I just ask you, if I just say that A transpose B is length of the projection, Then in this case it is true, because the projection is actually a into this particular quantity a transpose b, right? Since this is a scalar, this is a scalar, so the length of this will be actually given by the mod of this, right? Okay, so you can take this a transpose b outside, and the mod of a is actually 1, because this is a unit vector. Okay, so we can consider x. So Yashasvi is asking that we can consider x as a shadow that b will project on a. I'm not sure what does this shadow mean, but yeah, I hope you got it. It is basically the coefficient of a. Okay, that will tell you the projection, right? It is basically the scalar quantity by using which you will get the projection. Okay. Now suppose they give you this question and then they ask you to compute the projection. Okay, here they have used the C, they've used X cap. Okay. Anyway, this is another university. Can you do this? Right? So what is X cap? As we know, it is A transpose A, I mean length of A, and the dot product between A and B. So you write it like this or you write it like this, doesn't matter. I mean dot product, you can write in any way, it doesn't matter. Okay. Is this fine to everyone? Okay. Okay. So you can find out, okay, the projection. I hope now you know how to find out the projection of a vector onto another vector, right? Now suppose if I ask you that P is a projection of B onto A of B, right? It is important to know that it is a projection of B, not projection of A. I mean, not a vice versa, because the things might change. Okay, so it is a projection of B onto A. So let's suppose this is A, then this is a projection which is P, right? Now suppose they are saying what is the projection of B? They are saying that if you double this, okay, from A, if you do it to A, then it will still remain P, right? Geometrically you might see it, but mathematically also you can just put, okay, in the projection formula, you can just put, instead of A, you can just put 2A, right? Instead of A, you can also put 2A. Also, you can see here that doubling A does not affect P. So instead of A, if you put 2A, then it will be 2A into 2A transpose B upon 2A transpose 2A. Okay. So it will be just P, because this this 2 will get cancelled out, right? All of these two will get cancelled out. Okay. So I hope you understood this projection little bit, right? How to project a vector onto the another vector. Now, how to project a vector onto the subspace? Let's just find out it. Okay. Let's just find it out. So basically, currently we have seen how to project a vector onto just one vector. Now I want to see how to project a vector onto uh, a, a subspace itself, right? So for example, see, by the way, here I'm projecting B on A, and then I'm projecting B on 2A, right? Or maybe if you project B on, let's suppose, A by 2, okay, project B on A by 2, will it change? Will the projection change? Okay. So you project on A by 2, project on any multiple of A, the projection won't change, right? Why that is the case? Because the projection depend on the space, it does not depend on the basis of the space. Okay. Basis me like it might be little difficult to explain me everything here from linear algebra. So little bit terms, you if you might not understand, just keep on going. Okay, I mean you can watch linear algebra lectures later on for sure, but with this you just keep on going. Okay. I have already taken linear algebra, and that is also freely uploaded on YouTube. So let's suppose you are watching this as a non-enrolled student later on somewhere, then also you can watch linear algebra lectures on the YouTube. Okay. So anyway, What I'm saying, that either you project this b on a, or you project this b on a by 2, or this project this b on 2a. It doesn't matter. So basically the basis of this space, this is a one dimensional space. Do you all agree? This a is telling you one dimensional space, right? The whole thing is one dimensional space. So so on this 1D space, you choose any basis. You choose a, you choose a by 2, you choose 2a, you choose 3a, you choose anything, you choose a by 3. It doesn't matter, isn't it? It does not really matter that you are projecting on a or a by 2 or like that, right? So the basis, the choice of basis does not matter. Okay, it just matter that you are projecting on which space, on which, on this space you are projecting. That's all will matter. The basis won't matter. Okay. By the way, one of the student is asking, what if the b length is more and a length is less? So suppose b length is this, a length is this. Okay, and he is asking, will the projection be possible or not? So what do you think? Can you project b on a? Yes, it is still possible, and the projection will be actually having the more length than a. I mean, that's fine. You can just extend this a. Okay, I mean, geometrically you can extend this a. That x that you are getting. Okay, so basically you can say, I mean, the p that you are getting, it will be p, right? So p will be x a. So x that you are getting will be lesser than 1 or greater than 1. Tell me in this case. So here x will be greater than 1, right? It will be greater than 1. It and mathematics automatically take care of this. Okay, you don't need to worry about the geometry. Your mathematics automatically will take care of this. Okay, so while we are projecting, there is no notion of length. I mean, the length comparison between a and b. Okay, that won't be an issue. Sometimes the projection can be negative also. For example, if this is b, this is a, is the projection possible in this case? Tell me. Yes, projection is possible. Instead of a, you just take minus a. Okay, project on minus a. I mean, mathematics will automatically take care. Don't worry, you don't have to do anything. The p, which is x a, here the x will be negative. Okay, here the x will be negative. Automatically, it will be negative. Okay, automatically it will be negative. I mean, mathematics will take care all of these things. Okay. So coming back to this, so what I'm saying, the choice of basis does not matter, right? The choice of basis, either you are taking a, or you're taking a by 2, or you're taking 2a, 3a, a by 3, whatever you're taking, the choice of basis does not matter. Only thing matter that you are projecting on this space, on this 1D space, which is a, right? So here, if I'm projecting on this particular space, this particular vector space, then do you think the choice of basis will matter? The answer is no. Okay, the answer is no. Choice of basis will not matter. But just if you want, I can just take, for a special case, I can take the orthogonal basis, which means here, let's just take two vectors, which is u1 and u2. Okay, so let's suppose u and v. Let's suppose there are two vectors here, two basis vectors, um, u and v. Okay, and I want to project, let's suppose some vector t. I want to project this vector t onto this particular subspace. So this particular projection will be given as, earlier it was just x cap into a. I mean, the projection was x cap into a. Here also in the vector format, actually it is just in the vector format you can write the similar way, which means you can write ax cap, in the sense that a is your u and v. Is this fine to everyone? Here also you can write ax cap. Is this okay? I mean, the projection. Okay, the p. The projection, earlier also we have written ax cap. A, there the a was small. Here the a is I'm taking as a matrix. Here the a was vector. Let me know. Okay. Ax cap will be basically the projection. Anyway, the projection will be the linear combination of u and v, because u and v are the basis vectors. So the projection have to be the linear combination of u and v. Do you all agree? Because u and v are since basis vectors, so the projection have to be the linear combination of u and v. So you can write it as ax cap if you want to, right? Earlier we have written it small ax cap. Now you can write it capital ax cap, because this will represent the matrix of basis vectors. So a is a matrix of basis vectors, right? So this ax cap is a scalar or is a vector? What will be this ax cap? This is definitely a vector, right? This is a projection. Okay. So just tell me this vector. In the just like the previous way, can you tell me this vector? Just like the previous way, can you tell me this vector? This will be t minus ax cap, right? Or ax, whatever you want to say. Okay. So the same observation we can do. This t minus ax cap, don't you think it should be perpendicular to u and v, right? See, earlier we were saying this t minus ax cap is just perpendicular to a, but since these are the multiple vectors and it will be perpendicular to all of them, isn't it? Right? So so basically, see, the things will be exactly same. It is just that we are having the multiple dimensions. Okay, the things will be exactly same. Nothing will change. It is just that I'm just having the multiple dimensions. So earlier also we have done the same thing. If you want, you can make it as b. But earlier also we have done the same thing. But here also I'm saying this is perpendicular to u also. This is perpendicular to v also. Right? Yes. In fact, it is perpendicular to all the vectors in the plane, right? Of that is in the vector space that is formed by the basis u and v. That's the correct observation. Okay. In fact, this t minus ax cap is perpendicular to all the vectors. So basically, you can say, see, the things will be same. It is just that we now have multiple dimensions. Okay. Basically, you can say that t minus ax cap and u dot product is zero, isn't it? So if this t minus x cap is a vector and I want to have basically you can say that dot product of u and t minus x cap should be zero, right? So can I say that u transpose, okay, I'm just writing in the matrix format somehow. Okay, this is one vector only. T minus x cap is one vector. Can I say this and this quantity multiplication will give you the scalar zero, and this quantity multiplication will give you the scalar zero? Can I say something like this? I mean the dot this notation means the dot product, right? Which actually means the transpose, which actually means the u transpose and t minus x cap. Okay, so this is t minus x cap. Actually, I just wanted to see that how we can write in the condensed form. So this is t minus x cap. So actually, you can say this is a matrix which we can say A transpose probably, right? This is a matrix which we can say A transpose. So you can say ultimately that A transpose into this is just a vector. Okay, I mean I'm writing it as like a column vector. This is just a vector t minus ax cap is equal to a vector 0. Is this fine to everyone? Okay. So instead of t, I mean I don't know why I'm using the term t. टू बी ऑनेस्ट आई एम नॉट श्योर एंड ये मैंने ही लिखा था. लेट्स जस्ट बी कंसिस्टेंट. जो पहले भी बी यूज किया है तो अभी भी बी यूज करते हैं ना. सो लेट्स जस्ट यूज बी. ओके एंड आई एम नॉट श्योर व्हाई आई एम मे बी आई थॉट दैट you might be confused, but let's just use b is a better name here. Okay, is this fine? We can do it again, but abhi matlab do you think it's okay till now? Actually, the kind of settings that we are doing, we don't even need the columns of A to be orthogonal. Okay, for now. So from here, what you can say? Okay, isn't it giving you some nicer equation that you have probably already seen? This is A transpose A x cap equal to A transpose B. right? Okay. So by the way, can anyone guess why I'm using x cap instead of x? Can anyone guess? Any random guess? कुछ prediction that has nothing to do with the prediction or something. See, the only reason is that not to denote a scalar, or maybe I mean you may be having your own sort of regions, but actually whenever we see ax, okay, our mind, human mind just work like this. Whenever we see ax, we think it is b, right? We think this is equal, exact equal. I mean whenever we see ax हमें लगता है कि oh that is b, right? मतलब we have studied linear algebra, or we have seen this particular ax equal to b so many times that whenever we see ax, we immediately think it is b. Okay, we have to keep on convincing that okay, it might not be b, it might not be b, there might not be any solution like that, right? So just to avoid all of this clutter, I'm just saying x cap. Okay, instead of x I'm using x cap. So whenever you see ax cap, you should not see oh this is b. Okay, you should not see okay this is getting cancelled out. It's not like that. Are you getting my point? मतलब basically ax cap is not solvable. So I'm just having ax equal to b is not solvable, let's suppose. Okay, so I'm just having ax cap. Okay, so x cap, I'm saying the solution of this particular set of equation. X was the solution which was actually not solution solvable. So x maybe if that is solvable, then x I'm saying it is a solution of x equal to b. X cap I'm saying is a solution of a transpose a. X cap equal to transpose b. X cap you can say हाँ मतलब it is the best possible solution. Okay, approximation or the best possible solution. Anyway, it is just a notation just to make sure that you don't get confused that okay this is b, this is not b, right? So let's just do this exercise one more time if you want to, whatever we have done here. So do you want me to quickly do this one more time? Okay, and then I will just tell you that what is this, what this equation is, how this equation is helpful basically. So let's just copy this. It is actually easy only, just the same thing that we have done earlier. Okay, we want to project this b onto this space. Let's suppose this space is given by the columns of a. Okay, which means that the projection will be ax or maybe x cap. Okay, is this fine to everyone? The projection will be x cap because A is a matrix of bases. So anything here will be Ax cap. Anything here will be X cap. I mean anything in this particular subspace will be the linear combination of columns of A, right? Because this is actually containing the bases. So this particular vector will be B minus Ax cap. So you can say B minus Ax cap is perpendicular to the columns of A, right? B minus Ax cap is perpendicular to the columns of A, which could be U and also B, right? Okay. So ultimately, from here, you can say this U and V perpendicular actually means that U transpose into this just one vector, V transpose this one vector, which is B minus X cap. This should giving me 0 and 0, which means A transpose into B minus AX cap should be 0. This 0 is a vector or a scalar? What do you think? This 0? This 0 is a vector. Okay. This 0, this 0 is vector or scalar? This 0 is scalar, right? Because it is just a dot product between this and this, right? This 0 is scalar, but this whole thing I'm just writing just 1 0. Okay, this whole thing I'm just writing 1 0. Basically, it means this is a 0 vector. Okay. Okay. So anyway, like we have got our x cap, and how we are finding the x cap to solve after solving this normal equations. Okay, we call them normal equations. Is the x cap projection? Is x cap projection? No, right? So what is the projection? What is the projection? Ax cap, right? Ax cap. Okay. So for example, here you have something like this. Okay. So in this particular diagram, this is a projection, right? This is a projection, which is given as Ax cap. Okay. X cap is basically the coefficients which are making, I mean, basically we wanted to solve for the best x, but we were not able to solve for best x. So this is x cap is the basically the coefficients of columns of A, which means that that it is making the projection. Okay, it's like a kingmaker. It's like a kingmaker. Okay. So okay, so in today's politics, okay, I don't want to go in the politics, but yeah, some people might get offended or like that. But you okay, you might have heard for Bihar CM Nitish, right? You for Nitish Kumar, you might have heard that he's a kingmaker because he is basically contributing a lot. I think 30 plus seats in the NDA. So X cap is, you can say, Nitish Kumar. Okay. So he's a kingmaker, which means that finally he's making the projection. It is not like X cap is not the projection. Okay. X cap is the coefficient of columns of A, which is making the projection. Right. Okay. So this X cap is not the projection. Remember, this is the projection. Actually, this projection is also called as the closest vector that we can get in the space of this. I mean, this particular space, this particular vector space. So, so we also say that that uh, projection is the closest vector on the subspace for B, which means in terms of vector, if you want to understand, that's fine. But in terms of points, definitely you can understand. Let's suppose this is just 1 point. Okay, let's not worry about the vector and all. Let's suppose this is 1 point, and there's another point. Let's suppose there's another point. There's okay. There are many points here. Now, what do you think? What is the closest point to this particular green point? Which one is the closest point? If you want to go the closest, will you go in some other direction here and there, or you will go perpendicular? If you want to go to the closest, obviously you will go the straight, right? If you want to check the closest point, isn't it? So basically, if you this actually this is a perpendicular. Okay, this line is a perpendicular, might not seem like that, but yeah, this is perpendicular. Okay. So basically, if you want to have the closest point, you will go to the perpendicular point, right? So this perpendicular point is a projection, which is also the closest point. Okay, closest to B on this vector space. Is this fine? Okay. So why we have moved to this projection, it will get clear. Can anyone guess it by this point? Why we are moving to the projection? Because I want to get, let's suppose I'm in this subspace. I want to produce this B, which means let's suppose this is Ax equal to B. Using the columns of A, I want to produce this B. Is this possible? Currently, it seems like it is not possible. So what will I do? I will project this B onto the columns of A. Okay, I will project this B onto the columns of A. And then instead of solving for, you can say, instead of solving for Ax equal to b, what is the projection that we are getting, by the way? The projection is this p, right? The projection is p, okay, which is Ax cap. So So basically, what we will be doing, instead of solving for Ax equal to b, I will be solving for this. Here, x cap is telling you the coefficient to make this projection. Basically, I'm instead of approximating this b, instead of finding out, okay, what is the best possible b, I will say the, okay, what is the coefficient or what is the x cap that is getting me this p. I'm more interested in this p now because x is impossible. To get x, it is impossible. I want to get this p. Okay, so what are the coefficients of A which is making you P? This X cap. Okay. So basically, uh, I mean, you can say like this also. AX cap is P, right? So instead of solving for AX equal to B, I will be solving for AX cap equal to P, which means B seems to be impossible. So instead of B, I will make use of something else, which is actually possible. So what is the best approximation of B onto the subspace? P, right? Because P is the closest to the B. So instead of solving for x equal to B, I will be solving for Ax cap equal to P. Okay. Anyway, I will come to these things in a while. Okay. So currently, I'm just telling you that how to find out this x cap. So is this clear to everyone? Is this clear? That this is using this equation, you can find out the x cap, right? This is how you can find out the projection. Projection is Ax cap. Remember, projection is not x cap. Okay. X cap is like a kingmaker. Yes, these dots are data points. Okay. So let's just quickly see one more thing, which is called projection matrix. Okay. By the way, this projection matrix is also in the syllabus of GATE DA, as you can see here. This projection matrix is also in the syllabus of GATE DA. Okay. This is official GATE DA syllabus, and this projection matrix is a part of GATE DA syllabus. So, you might remember the projection, right? Projection was Ax or Ax cap, where the x was this. The projection matrix that we are interested in, basically the projection matrix is a matrix that, let's suppose you want to project this B onto this A. Then instead of doing all of this drama, I want to have something like this P, okay, which I'm calling capital P, which I'm calling projection matrix. Okay, it is corresponding to this A. Okay, which means if you want to project B, then this is the projection of B onto A. This is okay. Similarly, let's suppose you want to project C, then this is projection of C onto A. Okay, I want to find out such capital P कि उसमें multiply करते से ही I can find out the projection of that particular vector on the given subspace. Okay, this is projection of C onto A. So basically, I want to find such matrix that if I multiply with the vector, I get the projection. That's called the projection matrix. Will P, yes, P is the same. Okay, P is corresponding to small a, or the given vector space. P is same in case of small a, in case of this B and C. Okay, so this projection matrix is a part of official syllabus of GATE DA, by the way. Okay, so you know this, that we have got this AX. So X was this. So here, you can say these are the three. I mean, these are the vectors, by the way. But you can understand the vectors like the matrix also. These are the three matrices, and matrices are what we call it. associative, if I'm writing like this, we call it associative, right? So you can basically either multiply these two, or maybe you can multiply these two first. Okay, it won't matter. So what I'm trying to say here is that instead of multiplying these two, I can multiply these two first. And then can you spot the projection matrix? Yes, this is the projection matrix. So what is the projection matrix? This. Okay, this is the projection matrix. Because I'm looking, it is just a way of thinking. Okay, that's all. Projection matrix is nothing new. We have already studied this formula. It is just a way of thinking that, okay, let me take something such that only b remains on the right hand side. Okay, and I will call this as a projection matrix. By the way, this A transpose is not a scalar. This is a matrix. Okay, A transpose A is a scalar, but if you see A transpose, this is, let's suppose, 1 cross sorry, n cross 1, and this is n 1 cross n, then A transpose is a matrix. Okay, this is a matrix. So what is the projection matrix corresponding to just, small a? This is the projection matrix, right? Is this fine to everyone? Do you think it will depend on B? The projection matrix of A will depend on B? No, right? It will be just like this. If A is a unit vector, then the projection matrix will be, that's all, right? If A is a unit vector, then the projection matrix is just A transpose. That's all. Okay. Now let's just see the projection matrix for more than one dimensional space. Okay. So just like this, if it is a unit vector, it was A transpose. Just like this, if this is, let's suppose, I'm not proving it because we have done it in LA, so it's not a point of doing the same thing again and again. So if this is, let's suppose, you know, the more than 1D space, and here, if if the basis, okay, if the basis, so if basis is orthonormal, okay, which means that I have every vector length as 1, the orthonormal, right? If basis is orthonormal, then the projection matrix corresponding to that particular vector space is like this. Okay, if basis is orthonormal. Okay, just like this. See here, A transpose. Just like this, it is UU transpose. Is this basis orthonormal? Tell me. Here, if this is a unit vector, is this basis orthonormal? Yes, right? I mean, there are not more than one vector, but that's fine. Okay. So just like this, if the basis is orthonormal, it is UU transpose. Okay. By the way, tell me, is the UU transpose identity? If this is orthonormal, see, U transpose U is always identity. Okay. So U transpose U is, let's suppose, something like this. Okay. U1, U2. What is U transpose? U transpose will be, you do U transpose into U. So which means this into this. So which means U transpose this into this will be 1. This into this will be, what is this number? U1 transpose into U2, if this is orthonormal. this is 0, this will be 0, this will be 1. This is identity, right? What about the other way, which means u transpose u is u1, u2. Okay, so here it need not to be identity. I mean, it's not easy to see, but yeah, it need not to be. Okay. In fact, you can take some u, which is, let's suppose, 1 0 0 0 0. Okay, or maybe just three zeros. Some u1 like this and u2 like this. You can just verify. Okay, you can just verify. You take u1 u2 like this. You just multiply like this. You can just verify it. It need not to be identity. Okay, so basically this is not identity. Okay, some people get confused that if you use orthonormal that this is identity. Actually, this is not identity. Is this okay, everyone? So it is just like the previous case. Okay, I'm not proving it because it's not. It will be just a repeating of the same thing. But yeah, if this is orthonormal, then this is UU transpose. But what if the basis is not orthonormal? Can we have the projection matrix still? Okay, so this is just a last detour. Okay, if the basis is orthonormal, can we have the projection matrix? The answer is yes. Okay, let's just see how. See here that let's suppose the basis vectors here, I have taken u and v earlier, but let's suppose this is a1 to an. Okay, let's suppose these are the basis vectors. Okay, need not to be basis vector to be honest, but every vector here, right? Every vector here will be perpendicular to this particular, b minus ax cap, right? So basically, every vector here, a1 to n, I'm representing those vectors in capital A. These are the perpendicular, right? So we have done already this exercise, right? I have already shown you this. Okay, so from here you will be getting that a transpose into b minus ax cap equal to 0, right? So we have already gotten. Okay, so I can say, yeah, so we have already gotten this equation, right? Now from this you can say, if a transpose a, this is always, by the way, the square matrix a transpose is always a square matrix. You can check it. It is also the symmetric matrix, right? So if it is invertible, right? If a transpose is invertible, then you can write the x cap as this. Okay, x cap will be a transpose a inverse into a transpose b. This is x cap. If a is invertible, then x cap is this, and then a into x cap is this. Can you tell me from this what is this small p? Sorry, what is the capital P? Apart from b, whatever you are left with, this is the capital P, right? So the projection matrix is coming out to be like this. Okay. So when A is invertible, whenever you are having the basis vectors in A. Okay, whenever you are having the basis vectors in A, it is definitely invertible because basis vectors are linearly independent, right? Okay. So I will talk more about it, that when it is invertible or when it is not invertible. But is this fine to everyone that what we are doing? So let me just quickly do it again. So what we are doing, we have got our, this kind of equations, right? This is what we call normal equations. Now from this we are getting x cap. What is this? Now from this, can you tell me the projection? What is the projection? A small p, right? What is that? Ax cap. What is that? Right? Okay. From this, can you tell me the projection matrix? Once you have the projection, you can always have the projection matrix. What is the projection matrix? Anything apart from this b, right? Okay, this is the projection matrix. By the way, you can't open up this inverse inside because A itself might not be even a square matrix. Okay, A might not be square matrix, right? A may be rectangle matrix, so the inverse might not be even defined. So you can't take this inverse inside. Okay, don't take this inverse inside. So just to sum up that what we are doing, let me quickly give you the summary. If it is just one dimension, then we are getting projection PH small a x cap. Is this fine to everyone? Right? If it's just one dimension, yeah, one dimension. So this is A into, you can say it was A transpose B. I mean dot product of both of them. This was this, right? So instead of writing like this, I'm writing like this. Is this fine to everyone? For one dimension, let's just have for multiple dimension simultaneously. Okay. For multiple dimensions, we have got that that the x cap that we want. Okay, so this x cap is direct, but from for the multiple dimensions, the x cap that we are interested in will be found out using this equation. Okay, for the multiple dimensions, x cap will be found out using this equation. Now from here you can find out this p. Okay, once you have the x cap, every else step will be, I mean every other step will be same. So this is, sorry, this is capital A. That is the only difference, right? What is the x cap? Into A transpose B. Okay. So which is same as PB. From here, you can see capital P is, which is the projection matrix. Okay. Anyway, so have you understood this? Great. So basically, this is just for one dimension. This is for multiple dimensions. So how many steps are involved? You first need to find out the x cap, right? You first need to find out the x cap. Then you can find out the projection. Okay. If you want further, if you want, you can find out the a projection matrix also. Okay, if you want. Otherwise, that's fine. I mean, this is just optional thing. Okay, I just told you because that was in the syllabus, so I thought that I can just cover here. This is just optional thing. So if you want, you can stop here. Once you find out the projection, you can stop here. Okay, you can stop here once you find out the projection. Is this okay to everyone? So the projection matrix is just optional thing. Now you tell me what is the step to find out this x cap here in one dimension. Do you know, like perpendicular, using the perpendicular settings, I have found out the x cap, right? X cap is the main thing. Here here how we found out the x cap, using the similar things, right? Using the similar things, I have got this equation, and using this I can find out the x cap, right? Okay, so once you find out the x cap, then you can get your projection. Okay, projection and x cap both are the different things. Now let's just see some questions or some examples. Probably you will understand more. So by the way, this is the end of D2. Okay. Anyway, let's not worry about the projection matrix. At least the projection is fine. How we are finding the projection using just a small observation that okay, that this vector, right? This particular vector, right? This particular vector will be perpendicular to everything here. Okay, will be perpendicular to everything here. Using just this observation, we are finding out our x cap. X cap finding is very much important. Once you find x cap, the projection will be a x cap. Okay, let me know if that is fine. The projection matrix is something optional. You don't need to study this here. You're going to study this later on. Okay. Okay. Just give me a heads up. If this is fine, then we will move further. Or don't worry. Further also the same things might be coming. So you will get to understand more. Okay. So just for the quick question, suppose this A and B are given. Can you find out all of these three things? X cap, small p, and capital P. So Anurag is asking, can you explain what do you mean by dimension? Dimension means basically uh, here. I mean, actually, it will be clear, but yeah, it means the number of features we have. Okay, the number of features. So okay, so are you asking about this dimension of the vector, right? Okay, if you're asking about the dimension of the vector or dimension of the vector space, actually both are the different things. Okay, let's not go into much of this thing. First, let's just solve this question. Probably things will get clear. Okay, in just this lecture, things will get clear. Suppose this A and B are given. Can you find out all of these three things? How to find the x cap? To find out the x cap, basically the projection is A x cap, right? But the challenge is to find the x cap. How to find the x cap? X cap will be using the normal equations, right? Using the normal equations. So you can find out the x cap from here. Put in here. You will be finding the p, and then once you find the small p, then basically you can find out the capital P also. Apart from b, whatever you get is basically the capital P. So for example, this is A transpose B. Okay, you can solve for this normal equation. You will be finding the x cap. Your x cap is this. Now once you find out the x cap, they are saying the p equal to ax cap is your projection. So the projection is this, right? This is the projection. Now, once you get your projection, you can also get your projection matrix, right? The projection matrix is this. Okay, you can calculate this and then you will be getting your projection matrix. It is just a calculation based question. This question I've taken from Gilbert. Okay, so these are the three things. Is X cap projection? No. Is P projection? Yes. What is this capital P? This is just a projection matrix. Okay. Now, let's solve. Let's come back to our case and let's just solve for the least square solution. So basically, what we want to do, we wanted to solve for ax equal to b. Ultimately, let me just conclude. We wanted to solve for ax equal to b, right? But it was not possible. So what I can do, but it is not always possible, right? So what we can do, we can instead of solving for x equal to b, we can project this b onto column space of A, right? Is this okay to everyone? Is this okay? Let me know. Now, how to find that projection? We will be finding the projection using AX cap, right? I mean, the projection that we are looking for is basically AX cap. Okay. So instead of solving for B, I will be solving for AX cap. Basically, I will be finding out, you can say the X cap such that instead of getting B, I will be getting AX cap. Okay. So how to get this X cap? We will be getting the X cap using the, so we get X cap using the normal equations, right? Okay. This is the solution of X cap. So basically, instead of solving for X equal to B, I am saying let's just project B. Okay. So I will be getting some P. Okay. After projecting, I want to project and I will be getting some P, which is AX cap, right? So So instead of solving for B, I want to solve for, you can say, I want to solve for P, right? The projection. So, which means that instead of getting the B, I will be getting actually P, but not using X. I will be getting it using some other coefficient, which is X cap. Okay. So, I want to find out the best X cap, which is giving me the projection. Okay. We want to find out the X cap, which is giving me the projection, because we cannot find out the X, which is giving you B. Hence, we will find out the X cap, which is giving me the projection. So, instead of B, I want to get this P. So what is this X cap which will be giving me the projection? That is the whole question. Okay. Am I really interested in the projection? That's fine. I mean, that's useful. That might be useful in the projection. But instead of the projection, currently I'm interested in that. What are the coefficients that are giving you the projection? Okay. So I want to solve for X cap. Is this fine to everyone? And how to get this X cap that will give you the projection is basically using these set of equations. This equation, right? This is the linear algebra perspective. The calculus perspective was very straightforward, right? So this is also the straightforward in the sense that instead of solving for x equal to b, instead of finding out the x which will give you the b, I will be finding out the x cap which will give me the closest point to the b. Closest point to the b means projection of b. Okay, so I'm interested in the x cap. But the next question is that how to get this x cap, which is giving me the closest point to the b. So I will be getting this x cap by solving this. Okay. This is the best approximation of B, which means this is the closest point of B onto the plane that we are looking for. This is the best approximation. This projection is the best approximation of B, or in other words, this X cap is the best approximation of this X. Okay. So basically, if someone asks you to solve Ax equal to B, so what you will say? Maybe I might not be able to find out this X because B might not be lying in the column space of A. Instead of that, I will be solving for X cap, which will give me the projection, which means AX cap is finally the projection. Okay. So someone, let's suppose you solve for X cap and then someone say, what will you do with this X cap? Then what is your answer? AX cap is your projection. AX cap is the closest approximation of the B. Right? So, so once you get this X cap, you will say, okay. So maybe it is going little hard. Do you think it's very hard? Little hard is okay, but do you think it's very hard? See, actually, to be honest, it will be easy later on. I mean, unfortunately, this topic went little tough. I don't know why. I was not expecting that to be tough. Okay. But it actually, like later on, don't think in other way. In the sense that later on, don't think that okay, the things will be tougher. Actually, when we start linear regression, it will be easier than this. Okay. When we start logistic regression, it will be easier than this. Okay. So basically, I don't know why it became that way. Look, okay, I'm also, to be honest, not very much sure. But later on, the things will be easier. Okay, don't think that it will be tougher. Later on, things will be easier. Okay, so somehow this particular lecture is went a little bit hard than expected. But yeah, I'll just try to manage with this lecture. The next lecture will be easier. Okay, then I can say next the 4 5 lectures will be easier. Okay, easier than this for sure. काफी easy होगा. Okay, for sure. So basically, what we are doing, we wanted to solve for x equal to b, but we can't solve it. So instead of solving for x equal to b, I want to solve for something which is closest to the b. What is the closest to the b? P. So I want to solve for something like this, right? Something like this. So basically, I want to solve for this x cap, right? And how to solve for the x cap? Somehow I got to know that to solve for the x cap, I will be using this these set of equations. Once I solve for the x cap, And then someone asks me that what is the closest approximation you're getting, then I will say ax cap. So let's just solve this question. Suppose they ask you to solve this. Okay, so they are saying if the system is inconsistent, then compute the least square solutions. What is the least square solution? Least square solution is solution of this. Okay, least square solution is the solution of this. So definitely, answer is on the next page. You can compute. Okay, you can compute this A transpose A, which is coming out to be this, right? And then you can get it. By the way, do you think? Let's suppose I tell you this. Do you think that it is somehow, okay, by somehow, do you think that it is even possible to not project a vector on some subspace? Actually, this is not possible. I mean, basically the projection is always possible thing. Okay, the projection is always possible, which means that this p equal to ax cap is always possible, which means this ax cap is always possible. I'm just telling you intuitively. Obviously we will prove it mathematically also, that you always have the solution for this set of equations. So this set of equation is always consistent, fortunately. Okay, maybe x equal to b is not consistent, maybe it is inconsistent, but this is always consistent. We will prove it, but for now I'm just telling you intuitively why it is always consistent, because you have x cap here and x cap is always possible, the projection is always possible. Okay, yeah, if this is perpendicular, then the x cap may be 0, but it is possible. Okay, okay, if this is perpendicular, then the projection may be 0, but it is possible. It's not like you can't solve for x cap. Okay, so I hope you understood this. Someone asks you solve for least square solution, then they are actually asking you solving for this set of equations. Okay, so again they are asking you to find the least square solution for x equal to b. Can you do it? Okay, just try it as an homework. I think answer is on the next page. Compute A transpose A, compute A transpose B. Okay, so this is A transpose A. So here in this case it was A transpose B. So in the next question also, you can do this as an homework. You just need to compute A transpose A. This is something like this. A transpose B is coming like this. So now you can solve for the equation A transpose A into x equal to A transpose B. Okay, it is always consistent doesn't mean that it is always having unique solution. It may be having infinite solution also. Okay, it may be having infinite solution also. So I will talk more about it, but here in this case these are having unique solution, but it may be having infinite solution also. But yeah, important thing is that this is always consistent. Okay, this set of equations are always consistent even though x equal to b is inconsistent, because you can always project, you can always find the projection. Okay, you can always find this x cap, and how to find the x cap? Using this set of equations. Okay, yes. No, there could be multiple solutions, that's fine. Okay, there could be multiple solutions, that's fine. You can take just one of them. So suppose they are saying that write the normal equation and then find out the least square solutions using the normal equation. Find the closest point to the b. What is the closest point? Is this x cap? What is the closest point? What is the answer of this? Can anyone tell me? Closest point will be x cap, right? X cap is not the projection. Closest point is actually the projection, which is ax cap. Okay. So basically, you can find out A transpose A, you can find out A transpose B. Okay. And you can solve for this x cap, right? And the closest point will be ax cap. This is the closest point. Okay. So which of the following is a least square solution of x cap? So I think again you need to solve for A transpose A and A transpose B. Okay, after solving, you will be getting X cap. You can choose the answer that you're getting. Okay. Okay. Now let's just talk more about the properties of A transpose A, because this A transpose A is coming too many times, right? So for that, let's just solve few questions, one or two linear algebra related question, and then we will talk about A transpose A. So what they're saying, that prove that any arbitrary matrix A and B is having this kind of relationship. The column space of AB is a subset of column space of A. That's, I think, easy to prove. So suppose you will say X is in column space of AB. Then we want to prove that X is also in the column space of A. Or maybe let's suppose some other vector V. Okay. Is this easy to prove? I think yes, right? So if B is in the column space of AB, then what does this mean? V is actually ABX, right? Which means that A into something, some vector. Bx is some vector, let's suppose y. So it is anyway in the column space of, I mean, this A into y. It means that it is in column space of A, right? Is this okay to everyone? This implies that it is in the column space of A. Okay. That's very easy to prove, but yeah, just a question. That if you talk about the column space of AB and you could talk about the column space of A, then this is the relationship. The column space of AB is a subset of column space of A. Okay, let's just do next question. AB are the matrices such that product AB makes sense. I mean, that is the defined, which means the dimension wise it is defined. The null space of B is a subspace of null space of AB. So basically, they are saying null space of B is a subspace of null space of AB. Okay. So let's just no, okay. By the way, this question is true false, but let's just prove that to be true. Which means if some vector is basically here, which means if Bx is 0, then they are saying ABX is also 0. That's very obvious, right? Isn't it obvious? You can just multiply A both sides and then you will be getting this, right? Okay. So that's true. I mean, easy to prove. This. Okay. So you know that column space have this particular property. Null space has this property. We will come to to the conclusions in just a minute. Okay, let's just see this question. What they're saying: prove that rank of A transpose A and rank of A is equal. So for that, what we can do, we can prove in terms of the nullity. Okay. By the way, we have done, I think, these kind of proofs in the linear algebra. So I'm just telling you quickly. So suppose I want to prove. Okay. So what I want to prove? I want to prove that rank of A and rank of A transpose are equal. Okay. So that proof can be given using the null space or the nullity. Just spend 30 seconds or just 1 minute to read out this proof. This proof is easy. I will just come back in just a few seconds. Okay. So have you understood this proof? How many of you have understood? Okay. Have you seen this proof? Okay. So what they are saying, that they are actually proving that both A and A transpose A both are having the same null space. Okay. So which means that first they are proving that if X is in the null space of A, right? If X is in the null space of A, then by multiplying the A transpose, you know this. We have just proven this, right? But you can also prove otherwise if the matrix is not just AB. We have just proven for AB, right? But you can have A transpose A. If the B is basically, if this is instead of AB, I have A transpose A, then actually the nullity is same. So basically, if X is in the null space of A, then it is in the null space of A transpose A. That's how we can prove by just multiplying A transpose both sides. If this is the null space of A transpose A, which means if that is okay, then here we need to multiply a matrix which is X transpose. Okay, I mean X transpose is also a matrix, although it is a row vector, but it is also a matrix, right? So here we are multiplying which matrix both side? A transpose. Here we are multiplying which matrix both side? X transpose. Is this okay to everyone? Okay, X transpose multiply both side. Here A transpose. Now this you can write it AX transpose, whole thing, which means the length of AX, or if the length of AX is 0, then the vector has to be 0, right? Okay, and then it means the X is in the null space of A. So which means the nullity is same. Okay, so I mean one is some subset of another, which means nullity is same. If the nullity is same, then dimension of nullity is same. Okay, dimension of nullity is same. Sorry, null space is same. Then dimension of null space is basically nullity. If the nullity is same, then rank is same. So actually, this is very important result that you need to remember, that rank of A and rank of A transpose A is same. Okay, that's extremely important result. Okay, so this is very important to remember. Understood? Yeah, I mean, rank of A and rank of A transpose is also same, definitely. Okay, so you can actually replace A with A transpose in both of this equation. Okay, not just in one. You can replace with both of this equation. Doesn't matter. Okay. So basically, if you replace, it will become A. It will become A transpose, and then this will become rank of A transpose, which is also same as rank of A. Right. So you can replace in both of the places. You can replace A with A transpose. That's also fine. Okay. So is this okay to everyone? That both are having same rank, which means that A transpose A is invertible if and only if A is invertible, isn't it? Which means if A is invertible, then only this A transpose, sorry, not invertible. Basically, I can say A, the columns of A are linearly independent, right? Then it will be having the rank as n, and then this will also be invertible, because this is, if A is m cross n, then this is n cross n. Okay, then this is n cross n. So basically, this rank has to be n, right? To make it invertible. This rank n means A rank is also n. A rank n means columns of A are linearly dependent, right? So since both ranks are same, so A transpose A, dimension of A transpose is n cross n, right? Is invertible when rank is n. What does this mean? What does this mean? If A is m cross n, then columns of A are linearly independent. Okay. Is this fine to everyone? That to make this invertible, columns of A has to be linearly independent, right? I mean, this is just one property that we are seeing. Okay, because both ranks are same. Actually, you need to remember this property. This is very important property. Okay, now let's just move to the bigger question of the, you can say, the elephant in the house, that prove that it is always consistent independent of Ax equal to B. Okay, so this is the elephant that we want to tackle. that A transpose A X equal to A transpose B is always consistent, right? This is our claim. Intuitively, can you tell me why it is always consistent? Intuitively, because this X here, or maybe if you want the solutions, you can write X cap. Actually ये तो बस वेरिएबल का नाम है, x लिखो y लिखो, doesn't matter, right? So because this x is actually the giving you the projection, right? And projection always exists. So that's why this is always consistent, right? So intuitively, what is the answer? Let me write ax cap. I mean, doesn't matter. You can write by here, you can write x here. You know, this is just a variable, right? Anyway, you are solving for that variable. Okay. Okay. Intuitively, this gives you the projection, and projection is always there. So basically, what does this consistent mean? What does this consistent mean? That either unique solution or infinite solution, right? Either unique solution or infinite solution. By the way, tell me, if columns of A are linearly independent, okay, then tell me, can we say, this? What do you think? See, it may be possible this B is, out of the column space, right? I mean, you just have, let's suppose, two columns, just two columns, and then this B is obviously using these zeros, you can't get 3 4, right? So B may not be in the column space, right? So the answer is no. Okay. But if the columns of A are linearly dependent, then what else you can say about the least square solutions? Can you say least square solutions have unique solution? Always exist is not any good information, because anyway they exist, right? Then we have, right? Why? Yes, because very nice. A transpose A is invertible, right? A transpose A is invertible. In this case, if A transpose A is invertible, then we have unique least square solution. Okay. In that case, we have unique least square solution. If A transpose A is not invertible, then we have multiple least square solutions, but the solution are always exist. Okay. So tell me how to prove it. Okay. Let's just go proving about it. See, we have seen one thing. Okay. So let's go step by step. We have seen one thing. What is that? Rank of rank of A transpose A and rank of A is equal, right? We have seen this thing. Okay. Now, now the second thing that we have seen was, you can say that null space, okay, null space of A transpose A is a subset of null space of right? Now, using these two things, can we prove that the set of linear equations are always consistent? These set of linear equations. Okay, so let's just see. So, by the way, just a second. So here, which is actually same as rank of A transpose also, which is fine, right? Okay. So basically, if I want to show that this is consistent, then what I have to show is that that column space of, see, this is in the column space of this particular quantity is in the column space of A transpose A, right? And this is in the column space of A transpose. Okay. So suppose, just consider a vector which is in the column space of A transpose A. Then it is definitely is in the column space of A transpose, right? I mean, that's what we have already proved. Is this okay to everyone? Tell me this line. Okay. So now we have one thing which is the column space of A transpose A is a subset of column space of A transpose, right? This is what is okay to everyone. Now we also know that both are having the same rank also. Okay. Both are having same rank also. What does this mean? See, this A transpose is n cross n, by the way. This is also n cross. I mean, the column space basically will be, what will the dimension of the column space? If these are the m rows and columns, right? So I think the column space, I mean the columns. So basically, A is m cross n. So A is n, A transpose is n cross m. So, and this A transpose will be n cross m. That is fine. So A transpose A will be n cross n, right? Yeah. So columns of A transpose will be of dimension n, right? Okay. Sorry, I got confused. So columns. So since it is n rows, but m columns, right? Number of columns does not matter, but the columns here will be n dimensional columns, right? So here you have n dimensional columns, obviously, right? Is this okay to everyone? A transpose has n dimensional columns because m rows, but n columns. Sorry, n rows. So since they are having n rows, so that's why the dimension of the column will be n, right? So let's just take these two, just a 1 minute conclusion, and then you can easily prove it. It's not very hard. See, just using these two, what we can say that, see, here you have the ranks same, right? Rank same, which means if you have here, assuming, okay, assuming you have, let's suppose, let's not worry about the dimension of the column. I mean, it is consistent with both of this. It has to be consistent, which means here the columns are n dimensional, here also columns are n dimensional. Okay. So let's suppose there are five basis vectors here. Okay. Maybe of, let's suppose, 10 dimensional in RD, doesn't matter, in R10. Here also, how many basis vectors you will be having in R10? If these are the five basis vectors in A transpose A. Here also five basis vectors, right? So can you say that you cannot see whatever column you have here, right? The since the column space is subspace, so whatever column you have here, you anyway that have that column here. But can you have anything extra here? Can you have anything extra here? In A transpose, can we have anything extra which is not in the column space of this? Which means it cannot be formed using the columns of this. You cannot have basically the basis vectors if you have five basis because the ranks are same. Okay, since ranks are same, if you have five basis vector here also five basis vector. So in terms of basis vector, if I say you cannot have any extra basis vector here. So actually this is not just a subset. It is actually equal. Okay, so both column space of A transpose A and column space of A transpose is actually equal, which means whatever you can form using A transpose A, okay, whatever you can form using A transpose A, which means A transpose A, whatever column using this columns of A transpose A, let's suppose X, okay, this is some vector which you are forming using the columns of A transpose A. Then you can also form, since the column space is same, you can also form the same vector using the columns of A transpose. Okay, maybe the coefficients could be something else, which is B. Okay, so basically, in other words, if this is in the column space of A transpose A, then you can def A transpose because see, when this is consistent, when this is consistent, whenever, you can say that this is anyway in the column space of A transpose, right? This is anyway in the column space of A transpose. So when can you find this X cap? Whenever you can have anything in the column space of A transpose, you can produce that vector using the columns of A transpose A, right? So we can produce this vector using columns of A transpose A. Okay, we can produce this vector using the columns of A transpose A. It is always possible because both are having the same column space. Okay, A transpose A and A transpose. Basically, if A transpose can produce, then A transpose A also can produce. The coefficient could be X cap. So if you are giving me some vector produced by A transpose, then I can give you the same vector produced by A transpose A also. Coefficient may be little different. Okay, because both are actually having the same column space. So basically, if you want, you can read out this particular screenshot also. So basically, they are proving that both are also having the same column space. The things are same, exactly like exactly whatever we have followed, the things are same. Okay, so they will first prove that ranks are equal. Okay, or maybe they have proved that nullity is equal, nullity or rank, okay, whatever. So ranks are equal, this is the subspace using these two. So rank and the column space, right? Sorry, null space is actually same. I think by mistake I have written null space. Column space is subspace. Null space is actually same for both of these guys. Okay, so you can read it, or maybe there is, I think, one or two more screenshot I might have put it. So at any place, if you see the proof will be following the same thing, which means they will say that okay, rank is same, and the second thing is that the column space is a subspace. So basically, they are saying column space A transpose is subspace. Okay, this is the first fact and second fact. Using these two facts, you can prove that actually the column space is also same. Okay, okay, column space is not just a subspace; it is actually same. So basically, using these two claims, you can show that okay, column space is actually same. Okay, these are the three screenshot of proof. One, they are having the same idea. Two, and this three. Right? What is the idea? That if you are having five basis vectors here, you will be having five basis vectors here also. Okay, so you can just think about it, and then you can say that yes, this system of linear equation is always consistent. And also you can prove it using intuition, or you can have the intuition that okay, projection always exists, right? Cool. So let's just have one or two true false question before we end. Tell me, is this true or false? A 3 cross 2 matrix A and B, Ax equal to B, does not have a least square solution. Can there exist a 3 cross 2 matrix such that it does not have a least square solution? The answer is impossible. Ax equal to B always have least square solution. Okay. Let's just solve this question. So they are asking for false. So which of the following is false? The equation A transpose, this is always consistent. What do you think? Yes, this is true, I think, right? This is true. It is always invertible. Maybe false, they are asking. It is always invertible. This is false. When it is invertible? Only when columns of A are linearly independent. Okay. A is a solution. So basically this is false. So this is the answer. Maybe there are multiple answers. So let's just assume this is MSQ. A is a solution to this A transpose. This is, a solution to this is not a matrix basically. Is a least square solution of X equal to B? Yes, this is true. The columns of A transpose lie in the column space of A transpose A. Actually, the both the column space are same, right? So they will definitely lie. The columns will definitely lie here, right? This is also true. Then Ax minus B is orthogonal to, if X is a solution of this, then Ax minus B is orthogonal to the column space of A. This is nice. What do you think? If X is a solution here, they're not using X, which is fine, right? Yes. So basically, this X is giving you the projection, right? I mean, Ax is the projection. So Ax minus B is definitely orthogonal. So it is just like that vector, if you remember. This is Ax minus B. Okay. Yes, this is also true. Understood? So hence only B is the correct answer here. Okay. Yes, Ax minus B is nothing but projection P. No, sorry. Ax is projection P. Ax minus B is your perpendicular vector. Maybe I have the screenshot. Okay. So I hope you understood that this was the vector space, right? Here, this is the B that we are projecting. This is P. So this is Ax minus B. This is always perpendicular to the column space of A. Okay. Give the example of the matrix. A 3 cross 2 matrix that has more than one least square solution. Okay. So they are asking, can you give me that has more than one least square solution? You can give anything which is basically where columns of A are not linearly independent, right? If this is three rows and two columns, three cross two matrix, three rows and two columns. Okay. You just give one matrix, for example, any three cross two that does not have full rank. Like, I mean, for example, this is 1 2 3 1 2 3. This is the answer. Okay. So they are saying give any three cross two matrix that does not have that has more than one least square solution. So is this okay to everyone? Because I don't want column to be linearly dependent. I want them to be linearly dependent. Okay. Then the rank will be less than n because it is does not have full rank, right? So rank of A is basically 1, which is less than 2, right? So hence A transpose A is not invertible. Hence infinite solutions, infinite least square solution, right? Okay, so that's all. Basically, in this picture, I just wanted to show that we get the projection P, right? So this is the B. We cannot get B directly. So instead of B, sorry, this is b, this is b equal to 1, this is b equal to b2 equal to 1, b3 equal to 3. Instead of this b, okay, or this is 1 1 3, we are basically getting the projection which is 5 by 7, let's suppose 13 by 7 and 17 by 7. Okay, so suppose we are getting something like this. So instead of getting this b, we will be getting this projection p. So individually, if I talk about, instead of getting, b1 is the first number in the equations. For example, this is b1. Okay, instead of getting 30, maybe I'm getting something near to 30. Okay, maybe I'm getting something near to 30. Okay, so this is all about the linear algebra perspective. Hope you understood that what is a projection and what are these things. So basically, ultimately, we have to solve this equation, right? To solve ax equal to b. If ax equal to b is not solvable, then you can solve this. Otherwise, you can directly solve this. It will get the best solution. If the best solution is the solution of ax equal to b, then also it will get you this. Okay. So Navjot is asking, how will we find x cap in this case? X cap is basically just a system of linear equation, right? This is x cap you will be finding using the system of linear equation. I mean, you will not be able to invert it. So don't find using the inverse or something. X cap you can find using the system of linear equation. Okay, the way we did it in linear algebra, using the Gauss elimination or the Gaussian elimination. Okay. Okay. So that is all I wanted to discuss today. Thank you, everyone. Thank you so much. Okay. If there is any doubt, you can just let me know. Let me just pause the recording. I mean, if there is any good doubt or anything that I think that it should be included, I will again resume the recording as always. If I think that okay, this is okay, it will not. I mean, it will be just clear to probably most of the students. Then I will not include that particular doubt in the recording. So thank you, everyone. Let me just pause the recording. Thank you so much.